So, very good morning to everyone. So, we'll start our day two program. For this, I would like to request our Professor Tanmay Som. Please chair the session. Welcome you, sir.
Very good and warm morning to all of you. And let me introduce Professor Oscar Castillo. Professor Castillo is a professor of computer science in the graduate division, Tijuana Institute of Technology, Tijuana, Mexico. He holds the Doctor of Science degree in computer science from the Polish Academy of Science. He is also a chair of the Mexican chapter of the Computational Intelligence Society, that is IEEE. He also belongs to the Technical Committee of Fuzzy Systems of IEEE and to the Task Force of Extensions of Type 1 Fuzzy Systems. He is also a member of NAFIPS, IFSA, IEEE. He belongs to the Mexican Research System of Level 3. His research interests are type 2 fuzzy logic, fuzzy control, neurofuzzy, and genetic fuzzy hybrid approaches. He has published over 300 journal papers, 10 authored books, 50 edited books, and 300 papers in conference proceedings, and more than 300 chapters in edited books. In total, around 1,000 publications. He has been guest editor of several successful special issues in the past. He is currently associate editor of the Information Sciences Journal, Journal of Engineering Applications of Artificial Intelligence, International Journal of Fuzzy Systems, Journal of Complex and Intelligent Systems, Granular Computing Journal, and Intelligent System Journal. He is also an associate editor of Journal of Applied Soft Computing and IEEE Transactions on Fuzzy System. He has been elected as International Fuzzy System Association Fellow in 2015 and Mikai Fellow in 2016. So I don't want to be any hindrance between our beloved speaker, Professor Castillo, and our audience. So please, I hand over the mic to Professor Castillo.
Thank you very much for the nice introduction and also for inviting me to deliver this talk. Professor Som, thank you very much. Let me share my screen. Is it okay now?
Yes, absolutely okay, Professor.
Okay, thank you very much. So I will start then. So my talk on this time will be more on the side of describing type 2 fuzzy systems and also give some initial ideas about type 3, which is I think the future is going for that. And so I will just show some initial ideas on that for the people interested in this future research area. So I will give some details about theory and also some applications to keep a balance between both things for different maybe kind of interested people in the audience. So this is just a summary of what Professor Son was mentioning about my previous work. And this is my group in Tijuana. This photo was about 3 years ago in one of our meetings there. And we have an annual meeting of the chapter of the IEEE Computational Intelligence Society in Tijuana or different parts in Mexico. And okay, so let's start with the main things about this talk. So basically, just to put this in a perspective, of course, we can say that all traditional mathematical models are based on type 0 in the sense of the categorization that we use in fuzzy systems or fuzzy logic. Type 0 will be precise numbers in the sense of course, the work by Professor Sade, in which he proposed in 1965 what at that time he called fuzzy sets, then later fuzzy logic and fuzzy models. And later we can say that what he did at that time was what we now call type 1 fuzzy models, of course. Uh, and later also he proposed, I mean Professor Sade, in 1975, what he called type 2 fuzzy models. And there were some papers, 3 or 4 papers after that, dealing with type 2, but the area of type 2 remained almost without any development for many years until about 2000, the year 2000, when Professor Mendel from USC started working on this area, and also some of his students working with him, starting developed also some interesting things and some theoretical advancements and some algorithms. And later, other groups in the world started working also on type 2. And then after 20 years, almost 20 years now, we have that. Now is, I think, well recognized that type 2 can help solve many problems. And we have good results in comparison with type 1, which was important because at the beginning, people working on type 1 were questioning that it was worth it, if it was worth it to in interval type 2 or general type 2 fast system, because of course, in computing time, they require more time to be processed. I mean, type 2 require more time in processing. So at the beginning, this was a drawback, and we needed to see if we could have efficient implementations of type 2, and also at the same time, if the results will be sufficiently better with respect to type 1 to really be worthwhile doing this. So at the end, we did find that it was worth it, and the results were better, and at the end, not so expensive computationally speaking, also. And on the other hand, for applications, usually we need to optimize these systems. In general, when we design models, mathematical models or neural network models or any kind of model, usually for applications, we need to optimize the parameters of the models. So in this case, again, is the same thing. The same thing. I mean, in fuzzy systems, we need to for designing the optimal fuzzy system for a particular application, we need to find the particular best values of the parameters in the fuzzy system, also maybe the optimal number of fuzzy rules and so on. So the structure and also the parameters of the fuzzy system are needed to have the best results. And that's where optimization algorithms also help. In the case of us working on computer science and computational intelligence area, usually we also use methods from these computational intelligence techniques like meta-heuristic or bio-inspired optimization algorithms like genetic algorithms, particle sum optimization, and others. And that's also, I should say, very important, because if not, our fuzzy system maybe will not be competitive, because they will not be giving sufficiently good results. But now, with this optimization that we perform, these fuzzy systems are very competitive in many areas like control, robotics, pattern recognition, time series prediction, and others. So even with these successful applications, still we have in mind the question if maybe there are even more complex problems that require even better models than type 2. That's why I will talk about type 3 in a few slides later in my talk, because there have been recently in this last year some papers from us and other people in research that have also developed some type 3 fuzzy systems. And I think I will just give some words about that so you can get the idea. But so we need to consider that this is a possibility, and maybe this more complex problem or nonlinear, noisy, dynamic environments, situations for these problems will require this even more uh, powerful models. So here, the main contribution of my talk will be to describe these differences between type 1, type 2, and even higher types of fuzzy systems, how they can be applied, how can we optimize them. And the idea is that in particular applications that we have, we need to minimize the difference between the output of the fuzzy system and the real dynamical system. So the real dynamical system that we want to model, the fuzzy system or the fuzzy model will have to produce outputs that are very similar. So the difference measuring some metric will be minimized. So that's where the optimization is needed to minimize difference between the output of the fuzzy system and the output of the real system, real dynamical system that we want to model. And this is why the optimization is needed. So anyway, that's the main idea of what I will talk about. And I will start from the beginning, just for the ones that maybe are not familiar for of these concepts. And so I will start from type 1 and then go to type 2 and then a few words about type 3. That will be the idea of the talk. So type 1 was proposed by Professor Sade, as I was mentioned, in 1965 as an extension of the original idea of the traditional sets. Traditional sets, of course, coming from the Greeks before Christ, they allow just to have two kinds of membership. You either belong totally to a set or you don't belong. So, in other words, you have membership of 1 or 0, just 1 or 0, because you belong or not belong. There are no in between situations in between 0 and 1. So Professor Sadek, what he proposed was that this membership for real situations, human situations, they should belong, they should be between 0 and 1. Because in some cases, for many things that occur in the real world, maybe we cannot state just 1 or 0, or true or false, because this dichotomy is difficult. So we are forced in some way, arbitrarily maybe, to put a 1 or a 0, but it's not exactly that, only in extreme situations. And so that's why he proposed this idea. And later, of course, if as he generalized the concept of a set to propose a fuzzy set in this way, of this difference in this change in defining the sets, of course, the consequence was that also logic was generalized. So fuzzy logic is a generalization of traditional logic, and then all mathematics can be generalized also, because if you generalize this concept, then you can have fuzzy algebra, you can have fuzzy topology, you can have fuzzy differential equations, fuzzy integrals, and so on. So there are people, many computer scientists and mathematicians in the world trying to work on these extensions of all mathematics to the fuzzy area. So this is just the idea of type 1. But the idea was to represent uncertainty. We as humans, for example, we can talk about some things in our life, and we can talk about, for example, if a person is tall or is short or is old or is young. But when we talk in that way, is like something more subjective, and there is uncertainty in the meaning. Uncertainty in the meaning, not not in the random sense, like in probability. Here is the uncertainty in the meaning of the words. So this uncertainty was tried, the, 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 the idea of fuzzy set was trying to convey this uncertainty or to represent this uncertainty, but later, Clear and Joan, they showed that type 1 was not able to represent this uncertainty. It was just describing some kind of vagueness in some way. So that's the reason why type 2 was proposed, even by professors at the beginning. Let me show you an example. This is a simple example of a type 1 fuzzy set trying to represent the concept of tall people. The concept of tall, of course, is uncertain because for me, for example, tall will be different thing than for other people, or like in the audience. Some of you for maybe are thinking of tall in a different way. So that's why it's uncertain. And so when we say that, for example, John is tall or Jim is tall, it could mean different things for me than for you. And anyway, so in a fuzzy set, they try to represent the uncertainty of the concept we use in a membership function. In this case, it's a triangular membership function in this figure. And for a particular numerical height of the person, then with this membership function, this fuzzy set, a membership will be assigned. Of course, for a person that has a height of 2 meters, maybe the membership will be 1, because in that case, almost all of us will agree that the person is tall. But for other heights, other numbers, some people may believe that the person is tall, and others will not believe that. So this number will give us an idea of how tall this person will be in this for this concept of tall. So anyway, this is the idea in type 1. So this is not sufficient, because how can we give a numeric precise value to this if my meaning will be different than the meaning that any other person will give? So in fact, this is not a way to represent uncertainty. That's the reason why type 1 was not sufficient to represent uncertainty. And so in reality, what we have is, of course, this is an improvement on just saying tall or not tall, like in classical sets or traditional sets. It's an improvement because we are saying that we cannot give a number 1 or 0, just a number of 1 or a membership of 1 or 0 to this concept of tall, but the value that we give is not sufficient to represent the uncertainty of the concept. So that's why type 2 was proposed. So actually, what we want is something like about 0.62, because the value of 0.62 is some number that maybe is just a value, maybe it's like an average of what many persons, if we make a survey of this, the meaning of this concept, maybe some of you, maybe for 1.8 meters, you will give almost a value of membership of 1, and others will not give a value close to 1. So if we average what many persons will say about this, maybe this value will be the average. So, but even an average is not a good representation. So what people in type 2 did was to say, okay, we can give a meaning using an interval around this 0.62. Or even a more complete representation will be giving a fuzzy set to this value. So accepting that this value is not precise because it's not only one value, it's a different value for different persons, then we can give a fuzzy set to each point of the membership function that I represented before. So in this case, what we are actually doing is something like this. We will say, okay, some persons will give one value, others will give another value. So it's like saying that some persons will have one membership function, like the one here, dotted line. Others will have other triangulars inside this area. And so in some way, this area, this shaded area, what we call the footprint of uncertainty, FOU, this footprint of uncertainty will represent the uncertainty in the meaning of the concept of this word, okay, which is the word tall, which means different things for different people, as Professor Mendel says in his papers. Is represented in a better way using this shaded area. And so this membership function, not just a simple triangular function, this is a triangular but with a with an area, with a footprint of uncertainty, will represent in a better way this concept. So in this case, we will have an upper membership function, which is the limit function here, and a lower membership function, which is the inside one, the lowest one. So we have a lower limiting this function and an upper membership function, which are type 1 membership functions, limiting the type 2 membership function. So in this case, if we now use this type of membership function for a particular height of a person, then if we go to the membership function, we will have an interval. So we will say here that the membership of this particular height of 1.8 meters will be between 0.442 and 0.78, containing all the meanings of different people for this word. So, for example, people working in computing with words, which is another area, computing with words is based on assigning meanings to every word in the natural language in this way. So you use fuzzy sets, type 2 fuzzy sets, to represent the words of the language in English, for example. And then you can, in computing with words, you can process natural language, giving us inputs, a sequence of words, and then the output will be a sequence of words that will be an answer, for example, for a question or something like that. So, but that will be another area. I will not talk about natural language here, but people in that area also use fuzzy sets in this way, using words as fuzzy sets. So let me go back just for the mathematical definition of the interval type 2 fuzzy set. So in this case, what we have is that this fuzzy set will have elements, X elements. This is a representation. We have a membership function for each value of X. And then for this one, we have another membership function, a secondary membership function, which in this case has a uniform membership value of 1. So in this case, we have a primary domain for the variable and a secondary domain. This function is like a type 1 membership function, but for different values in a range. And the secondary membership is 1. So that's the reason why we have this kind of area here. Actually, it's a 3D membership function, but the third dimension, I will show you later another view of this. That in the third dimension, the secondary membership is 1, fixed uniform value of 1, so we don't need to show the third dimension in this case for interval type 2. So anyway, this is the representation. And so what we need here is then to have a way to calculate or to compute for a given input. If we have a fuzzy system, how to compute the output, we will need a part or a part of just using the falsification, which is the usual way to process type 1. We will also need type reduction, which is a way to reduce from type 2 to type 1. So this extra step was the one that was the bottleneck about 20 years ago. So even if we have the idea of how to have these fuzzy sets, this type 2 fuzzy sets and these two type 2 fuzzy systems, it was too slow in the computers at that time, for example, in 2000 or 2001. And the reason was mainly because this type reduction requires in some way to reduce from type 2 to type 1. So it's like we need like a weighted average from type 2 to type 1. That's the problem. Now it's not a problem, but at that time was like a computing bottleneck for us, and we were in some way in a problem of computing in a quick way this type reduction. In part, this was solved by a theoretical result. That time, Mendel and Liu, they were able to show that for computing interval type 2, two type 1s were sufficient to approximate an interval type 2, solving in some way the problem, because then if you can find these two type 1s that will approximate the interval type 2, then you can compute very quickly the result of a type 2. And the solution was like in this figure. I will skip many derivations, mathematical derivations here because of time. But basically what they found that it was that, for example, for this particular example of this memory function for toll, to approximate this function, we will need two type 1s here, the red one and the green one. Basically, the red one is part of the upper membership function, the limiting upper membership function. Then you switch to the lower membership function. In this point, this switch point is the left one, CL. And then the other one is part of the lower function, lower membership function, limiting function. And then you switch to the upper one. These two switch points are the solution, because if you find them, then you know where to switch, and then you can have the values of these functions, and then you can average, you can perform an average between the two type 1s, and then the problem is solved. So what they found was an algorithm, an iterative algorithm known as the Karning-Mendel algorithm, which iteratively approximates the position of these two switch points. And usually in 3 to 4 steps, you get a very good approximation. Then you can perform the average, and then you obtain the result. And this was even implemented in hardware at that time to make it even faster for control applications, because even with this Karning-Mendel, maybe for having real-time solutions, for example, in robotics, it was even slow. So for achieving very good results in real time, even hardware implementations were obtained at that time. So that's the idea, just to give an idea of how this is done. Of course, now at this time this was about 20 years ago, the derivation of the Karning-Mendel algorithm. We have more than 10, even maybe more, methods to calculate type reduction, and even direct methods for type reduction. I will show you some of them, involving or not requiring even iterations. So if you have a formula to directly compute the type reduction, it's even faster. So mathematically, you can find equations for doing that now, and this is even faster now. But anyway, this is the structure of the type 2 fuzzy system, in which you can see the idea of, in general, of a fuzzy system. Even for type 1, this is the idea. Just in type 1, you will not have type reduction here. But usually what we do is we have values entering the fuzzy system. We fuzzify. Here we use the membership functions with the inputs, with the values. Then with these numbers, we have that, for example, is low or high, or depending on the membership function that we have for the fuzzy sets, with some membership value. And we can compute with fuzzy rules a decision. So if you view it as a decision-making method, this is a way to calculate with the fuzzy rules. Do you perform inference with the logical inference method that we have in this area? Then you can obtain outputs as type 2 fuzzy sets in this case. You perform type reduction, like with the Karning-Mendel algorithm, to obtain a type 1, and then you defuzzify to obtain a number. For example, in control, if you are controlling a robot or controlling a vehicle for autonomous navigation, basically you are measuring values from the variables like velocity, distance, and so on. You have sensors. These sensors recopilate the values from the environment. Then you fascify, you have the fuzzy rules to control the robot or the vehicle. Then you do type reduction, the falsification, and then you have the output. How much force to apply, how much acceleration to put into the car, for example, if you are considering a autonomous vehicle, and so on. So basically, you can obtain the outputs in this way, but this is simulating in some sense the way that humans, for example, will drive a car. A human person driving a car will see the thing happening around and has the inputs of the same thing, the distance and the velocity and so on. In the brain performs the reasoning, then something like this occurs, and you, for example, push the accelerator of the brake or and so on, a particular force. So in some sense, you can view it as you are falsifying when you see the things happening outside in the environment. Then you do reasoning, then you defalsify to push the brakes or the accelerator or the wheel and so on. And this is done every second you are, or even faster, you are viewing the outside and you are doing your decisions and you are doing the actions. But even for other kinds of applications, like for example, in prediction, you can give inputs, you can have rules for predicting, then you can even have results here, intervals for the prediction, not even just numbers. Or if you are doing diagnosis, you can have rules for diagnosis, and you can have the particular diagnosis for particular symptoms coming inside, and then you can have diagnosis. And so this is in general framework. So just to continue with the generalization of the fuzzy sets, if now we consider that the secondary membership is not constant to 1 or not uniform value with 1, and we can consider that for any point, each point, I should say, in the range of X or the domain of X, you have a membership that is fuzzy again, not a number or not an interval like in the previous case, but a membership function for each point. Then you have a real general type 2 or complete type 2, as he said, like in this figure. So in this case, you see in this plane, this will be like interval, but in this case, we assume that in the third dimension, in coming out of the plane, the membership is not constant to 1. So in interval type 2, the one previous case I have explained, membership is assumed to be uniformly valued with 1 in the third axis coming out here, coming out the screen here, and so we don't need this axis because it's uniform. So we just plot this in the plane in like an area, but in this case we have 3D, so we have volumes in this case. So this is the general type 2. So this is even more challenging to compute now. What we do is basically we use alpha cuts or alpha planes horizontally or vertically, and each one will give us an interval type 2. And then we do the union of all interval type 2s to approximate a general type 2 in a general way. But on the mathematical side, we have very interesting thing because all mathematics that you know and logic and so on is generalized or extended because you have to extend operations of sets like union, intersection, and complement, and so on. Here they are called meet and join instead of union and intersection. And also this, as a consequence, has that you generalize relations, functions, and then all mathematics has to be generalized or extended with these concepts. But I will not go into that line of this area of the evolution of these fuzzy sets in that area. Let me show you very quickly, just to maybe be more convincing about my arguments, to show you that type 2 can actually produce better results than type 1. So basically, just the motivation, of course, in applications is that uncertainty occurs in almost every area of real life. So comes from many reasons like incomplete information, imprecise information, fragmentary, not reliable, even contradictory information, and many other deficiencies. Even if we are basing our development in a mathematical model of a system, mathematical models usually don't have all variables of the problem. So if you are not managing all variables of the problem, so you have a limited model, and so there is uncertainty in the modeling even. So anyway, there are many reasons. So just in this case, I will show you one situation, a particular situation in control. We assume that we have a controller with two inputs. Usually in control, we use the error that we have in a particular moment in time in the control. Think of it about like error in velocity, for example. If you are controlling the velocity of a vehicle, like with the cruise control, you have when you don't have the ideal velocity, you have an error between the actual value of the velocity and the real one. So this is the error. But also you can have the change of the error or the derivative of the error, which is how the error, if it's the error is decreasing or is increasing. This will be this information. And the output will be how to control, for example, in the case of the velocity, like when we are driving, we will use the accelerator or the brake to even or increase or decrease the velocity. So we can actuate over the system, like when driving a car, as humans. But in the case that this is done automatically in the car, this has to be done with the cruise controller, for example, in the vehicles. Just an example. It can be for any application. So we have on the left membership functions as type 1 for the error, change of error in the control. And on the right, the interval type 2 versions of the same ones. You can see that they are similar, just they are perturbed or they are expanded with a particular footprint of uncertainty. This area, if it's small, the results will be closer to type 1. If the area is wider or bigger, then you have more difference in the results with respect to type 1, of course, because you can, of course, imagine that if this area tends to, or you are tending to 0, then the results of the type 2 will be similar or even at the end, in the limit, be equal to type 1. So let me show you what happens in control. In control, usually you have your fuzzy system here, type 1 or type 2. The output is, for example, consider driving a car. Let's consider the accelerator. You are pushing the accelerator with certain force. And so the car or the system will respond with certain velocity. Then this velocity is measured and is sent back to be compared to the ideal velocity. The ideal velocity is the velocity, for example, that we want to maintain. Then the difference between this value and the ideal one will be an error. And also, if we compare the error at this time with respect to the previous one, we will have the change on the error. And these two inputs, we will have here fuzzy rules, depending on the error is going, is a small value, a large value, or depending on that, we will have different actions here to be actuated or done over the system. But in real situations, we have noise here. Not only here, we can have noise here also, and also in the model. Or, for example, if we have if the road is not horizontal, you have you are going up or downhill, then you have gravity actuating over the car. So you can have more variables here. But we will only be assuming that we have noise when sending the signal from here to here, Gaussian noise. So with this equation, and this is the mathematical model of the plant. So what my student did at that moment about 10 years ago was that To measure the error, we have metrics in control, metrics for measuring the error. These are the metrics usually used in control, square error or absolute value of error or time multiplied by the error. And we consider comparing when there is no uncertainty or no noise in the feedback. Of course, this is not real because in real world, we have a noise all the time. And here, of course, the difference between type 1 and type 2 will not significant. But if we have noise on the feedback, then we will see the difference is significant. Type 2 will be better than type 1. And for more noise present, the advantage of type 2 will be bigger. And if noise is very small, then type 2 and type 1 will be very similar. So that's the picture. So here we have no uncertainty. You can see the in blue type 1 result and in red the type 2. So there are some differences, but not significant difference. And then if we consider this noise in the feedback when sending the signal of the measured velocity, for example, then we can see this is more dramatical, the difference. You can see in this metric that the blue one, which is type 1, is for the time that we made this simulation from 0 to 200 seconds. Difference is very, very big. And we can calculate the errors overall this time. And we can see in the table in the following slide that the differences are very, very large. And so there is a significant difference. And if we increase the level of noise, it's even bigger. So that was the important thing about this paper that was published about 2009 in Information Sciences was the first paper showing that the actual difference were significant when using type 2 in control over type 1. And you can see here, for example, the total error with this metric with uncertainty is very different, or even in this metric, not too big, but this is a difference. And with even higher levels of noise is a bigger difference, even larger. So also in the trajectory of the controller, we can see why the errors are lower. If we are trying to have these particular values in the dotted line, the difference, the actual system is closer here on the right than on the left. So that's why type 2 outperforms type 1. Later, this was also done with real robots and real systems, and even bigger differences, because with real systems, here is like having a mathematical model of the system. It's a simulation. But in real system, there are bigger or larger differences because you have more things that you are not considering in a mathematical model. So this is just was important to show that it was something that could be done and good results can be achieved. So anyway, we also developed our own software about these years, about 2009, 2010. There was no type 2 toolbox and later there were other proposals in groups like in United Kingdom and Iran and Turkey, other toolbox. This is our own toolbox developed in our group. And now 2020, you can find a toolbox finally. MathWorks in the Physiologic toolbox has a type 2 toolbox in 2020 and up. And so, but before that, there was no commercial toolbox for type 2. So we developed our own software, and you can see that we have, like in MATLAB, we have to develop our own triangular, trapezoidal membership functions and Gaussian. We have more parameters in type 2 because of these areas. We need more parameters to represent these membership functions, like in when you compare with type 1. Anyway, but you have here that you can develop your fuzzy systems in a similar way. For example, this is for the shower control example, which is a benchmark control problem, controlling the cold and hot water in the shower. We do all the time this in our home, and we can be like an expert, but automating this is a nonlinear problem because of the flow and temperature of the water. And so even in this case, the example of in type 1 that was you can find in the type 1 toolbox, we did convert it to type 2 and in this way with the membership functions and the rules. These are the same as in type 1. And even in this simple problem, you can have lower errors in temperature and in flow, in the flow water with type 2 with respect to type 1. You can see here, for example, type 2 result, type 1 result. And also I can say that this fuzzy system is not optimized. It was found just by trial and error by us. So anyway, here you can see that briefly some of the recent developments that we have achieved. Like for example, this is on a paper where we propose type reduction with direct formula, the direct equations that derived by using Newton's method. We can obtain closed form formulas for type reduction. We can also approximate using that the fuzzy systems for parameter adaptation in metaheuristics. Also, we study the robustness with respect to noise of the controllers, where conclusion is that type 2 is more robust for control, which means that type 2 controller can accept higher levels of noise and maintains the optimal results, the good results for the control. And the reason is that you have like many type 1s inside a type 2. So each type 1 contained by the type 2 will be able to solve the problem for a different situation. So in some sense, you can respond to different situations in real world with a type 2 in a better way. And this is in this paper. And also recently we have considered combining the concept of shadow sets proposed by Professor Pedrich with type 2, because in this way we can approximate type 2 with shadow sets, consider two approximations of a set, and we can use that to improve efficiency of results. We have also developed theoretically a way to integrate alpha planes for approximating general type 2. In some way, we need to find a good way to combine the results of the interval type 2s that are obtained with the alpha planes to obtain a good approximation for general type 2. This is another paper where we use a sample of type 1s. Like you can see here, there are many type 1s. And with these samples of type 1s, we construct the type 2. This was applied to for classification, also for diagnosis, and this other paper, optimized in this case with pure particle sum optimization. Now, just a few words about type 3, just to give you an idea where this is coming. Here, what we now are doing, if we consider what I was saying before, now we have an element X of the domain. We have a primary membership function, then a secondary membership function, and then a tertiary membership function. You remember for type 1, we have only these two. Then for type 2, for interval, we have one value, a value of 1 here. But later for general type 2, this was a membership function. Now we have a tertiary membership function here. So this is a simple extension of the previous concepts. And now we have something like this. We have these kinds of membership functions. If we consider this, we slice it with alpha planes, we have something like this. And we can have the operations of sets and so on. And I will skip this, not enough time here, but we have applied to control with some of my colleagues in Iran. We have applications in control where basically just to give you an idea, in general type 2, as I was mentioning, the secondary membership is type 1. Now here, the secondary membership is an interval type 2. So that's the difference. In general type 2, the secondary membership is type 1, but in this case, the secondary membership is interval type 2. And this is another way of viewing this. So we have tested in control, real system, temperature control, this approach. And we have seen this paper was published this past year. And you can check it in the literature. We have about 3 papers on this, and we can have good results with this. I will not show more details. You can find it in the literature. And also, just my time is almost up. I will just show you quickly some applications. This is for controlling a robot, which is an omnidirectional mobile robot. We have the mathematical model. We have the controller in type 1 using sensors, the proximity sensors, and then here controlling the velocities of the 3 motors that we have in this case. This is translation or extension to type 2. We have here in this case a type 2 fuzzy controller in Simulink in this case for simulation peers, and then real system was tested. Here is the structure of the fuzzy system, 4 inputs of the 4 sensors and 2 outputs for this particular robot called Robotino in this case. This is for type 1. My student did it in the master degree for type 1, and then in the PhD he has been doing it for type 2. And this is the architecture for type 2. This is the particular membership functions of the type 1 inputs of the sensors and the outputs. The rules in this case, as there are 4 inputs, there are more rules than in other examples. The surface of the controllers. Basically, the idea is that the robot has to avoid obstacles and also follow a particular path or trajectory that we give the robot to follow to reach a goal, but also has to avoid obstacles. In simulation, this is some of the simulations that we have. This robot has this software for simulating like worlds of robot worlds, and you can measure your performance before testing with the real system. Actually, here we can find that type 2 controller will, for example, for this particular path or trajectory, it can be done in less time with a higher velocity, because you can make more smooth movements around the trajectory, and the errors with respect to the desired trajectory are lower. Very different, significant difference between the errors in type 1 and type 2 for all the metrics. And also in the real system, we have done it. So just to conclude my talk, so I hope I have been able to get interest from your side on this area. You can, like me, you can be thinking of applications, or other people in this area think more on the theoretical part. So on both sides of this research, there are many things to do. On the theoretical side, there are many things of the algorithms or the results, or performing a better way, or defining a better way the operations, or the mathematics behind this, or also in extending concepts in mathematics using fuzzy ideas. Or the applications are many to do to solve for real problems. So hopefully you will maybe work on this for some application or in the theoretical side. So thank you very much.
Thank you, Professor Castillo. Professor Castillo has wonderfully explained the different concepts of related fuzzy concepts type 1 fuzzy concept, type 2 fuzzy concepts, then fuzzy control, the error, what we have not heard earlier, now the error function associated, and then some noise, then fuzzy logic, and all the toolboxes, what he is developing for the uh, human use. Okay, many good examples, and the what is called the new dimension of walk, new dimension, that is from type 2 to type 3. So let us give a big hand to Professor Castillo. And if one or two questions, we do not have time to have questions because another session. Yes, only one question, please.
So, thank you, Professor Oscar Castillo. Many thanks for your innovative talk. So I have one question to you. Today we have published the paper with the help of type 2 fuzzy logic. It's true what I did only because of Professor Oscar Castillo after meeting IIT BHU. So I have facing one problem when we are writing some rules by when we are writing the programming part. So we are writing by ourselves. Is there any other technique so that from data set we can write the rule, fuzzy based rule? Is there any way?
You mean having data and
Yes, yes.
extracting rules? Yeah, there are methods. There are several methods, but usually what they do is they do clustering, and then with the clusters you can define one rule for each cluster. I think in one of the books of Professor Mendel, you have this method. And other authors have improved on the original idea, but the basic idea is that you can cluster data and then you can propose one rule for each cluster. And of course, maybe in some problems it could be that many rules could be proposed. So that's why other authors have tried to make this more efficient. But basically, that's the approach I will take. So,
are you if we use some type 3 fuzzy, so can we apply the arithmetic operation, addition, subtraction in type 2 fuzzy? If the number is the type 2 fuzzy number, so can we apply arithmetic operation?
For the question is for type 2 or for
type 3?
Is similar. Of course, there's still many theoretical work to be done.
Okay.
Right now, there are few papers. Maybe you can check on that. But I think in the next years, all of these things like fuzzy numbers or other things that we have done in type 2, first in type 1, then in type 2, will be done also for type 3, I think.
Okay, thank you.
It's just beginning. Okay.
Okay, sir. Thank you again. So I think we should go to the next speaker's talk. Now,